Okay, let's take a look at the second part of our overview of collect, which is the terminal operation that's most common. And we're going to talk about some of the most common predefined collectors that are in Java that you get out of the box. And you can see, again, this is from the EX12 example that we've been using for the other discussions. So here's probably the most common collector that comes out of the box. It's the list collector, and you get it by using collectors.toList. I imported the collectors interface or class, so it's not necessary to show it here, but that's what this is. That's where this is coming from. ToList is a factory method that's defined in the collectors utility class. And what that does is it takes every element that's in this stream, and you recall this is the stream of the Hamlet characters modified as usual, and we're going to collect those things into a list. So we'll end up with a list of strings, and because it's a list, there could be duplicates, like the clone army from Star Wars. You could have duplicates in here, and that's perfectly okay, because that's what a list does. It just stores the items it's given. It doesn't try to do anything fancy schmancy to make them have no duplicates and so on. Notice something else that's important from this use case, especially when you compare and contrast it to the for each operation that we looked at earlier. Remember, for each had the side effect, and we talked about how you had to make sure you initialize the local variable if you wanted to do that hacked up way of having a side effect to store each element in the stream into a local variable and all that nonsense. Well, the nice thing about using collect is all that accidental complexity goes away, because toList does the allocation of the list rather than us having to remember to do it earlier. And as a consequence, we can write this in a way where we don't have to think at all about whether or not there's actually going to be memory allocated. So that's one really nice thing about this. Another nice thing about this is it's absolutely trivial to change stream to parallel stream here and then have this whole thing run in parallel. Now, for this particular example, it's quite overkill to run this in parallel. But if you imagine us having a much bigger input set and a lot more processing, that could be a win. And collect works nicely whether or not what we're doing is running sequentially or in parallel. So those are two reasons why collect is just a big win over the for each operation we looked at earlier. And that discussion I just had is going to apply to all the other examples of collectors we're about to look at here. So that's basically the point I was just making. So collect is a lot less error prone, since initialization is implicit, and it's also thread safe and can run in parallel quite nicely. Another kind of collector that comes out of the box that's not uncommon to use is the set collector. And you get that by saying collectors.toSet, or just toSet if we import collectors utility class higher up in our program. And the main difference, of course, between a list and a set is that sets cannot contain duplicates. So now we're just going to have individual characters if we're doing Star Wars stuff, keeping with our Star Wars theme. We don't have the clone army of duplicates. We now have unique things. And as a consequence, that's the behavior you sometimes want. Now, if you don't want that behavior, then a list will be better because it's faster to add something to a list than it is to insert something into a set, because you have to, a set's implemented typically by either a binary tree or by some kind of a hash table. So it's a little bit more expensive than just tacking something onto the end of the list. But sets are useful things. And we'll see lots of programs where sets are very valuable and informative. Yet another kind of collector, which is more interesting and more complicated, is the map collector. And there's a bunch of different factory methods defined in the collectors utility class that makes maps in various ways. This is kind of the simplest way to do things. And what this does is this collector, the toMap collector, will collect the results into a hash map, which is a map, and it'll also keep track of various things like what are the keys, what are the values. So here's what this means. In this particular case, remember we've got Hamlet, the characters in Hamlet start with H, right? And so by putting the function identity method here, this says make the keys be whatever's in the stream at that point. So the keys in the map will be the characters in Hamlet that make it through the stream filters and so on. The next method reference passed here, which in this case is string length, is used to define what the values are in the map. And in this case, the values in the map will be the length of the names in bytes. So Hamlet, H-A-M-L-E-T, that's going to be 6, right? And Horatio is going to be 7, and so on. So it's a mapping of the name as a string to the length of the name. That's the value. And this last funky thing here is what happens if there's a duplicate, because maps in Java don't allow duplicates for a wide range of reasons. Unlike C++, where there's a concept of a multi-map, there really isn't a concept of a multi-map in standard Java. Of course, you could implement one if you wanted to. And so if you end up with two characters in Hamlet that have the same name, which actually occurs because there's Hamlet the father and Hamlet the son, and there's Fortinbras the father and Fortinbras the son, which is always very confusing when you first read the play because you're like, what the heck is going on here? What they're going to do is, since you can only have the name appear once, we're going to sum the length. So Hamlet would probably end up with the value 12 if Hamlet appeared twice, because we'd add it. And here's what a map looks like by default in Java. Java Collections Framework contains maps. And it basically has this hash table, if you're familiar with hash tables from your data structures courses. And you compute the hash on whatever the key is, and then that takes you to some element in this array, this table. And then what is there is either a linked list or a binary tree that's going to be preserved in essentially the effective order to make the searches as efficient as possible. So an ordered, balanced binary tree. And here's how things work. When you first hash, the so-called collision resolution algorithm will just chain things together in a linked list. But if it turns out that the linked list starts to grow and grow and grow, the concurrent hash map implementation, and I think at this point probably the regular hash map implementation also, will convert the linked list into a balanced binary tree. And that's to avoid pathological conditions where everything's hashing to the same value. And then you'd end up with basically a linked list, which is bad if you remember your hashing theory from data structures or algorithms course. So it's pretty cool. It'll turn it into a balanced binary tree, which means that no operation will ever be worse than log n time. So when people tell you, oh, the problem with hashing is that it's got linear worst case behavior, you can say, no, not if you implement the hash table in a clever way to have an array of references to balanced binary trees. Then it basically becomes no worse than log n in the worst case, even if everything hashes to the same location. And most likely will normally be much better than that, because everything is unlikely to hash to the same location. So that's what the toMap factor method does. There's also some other variants, such as the grouping by factor method, which has some things in common. You identify what you want the key to be. But unlike toMap, which will always create a hash map, grouping by allows you to provide a constructor reference for the kind of map you want to have made. So we might, for example, want to have a tree map instead of a hash map. And as you might expect, a tree map is implemented as a balanced binary tree as opposed to a hash table. And then the third parameter here, well, let's see. Let's first walk through these things. So the first parameter is the classifier, and that's basically what figures out where the keys are going to go. And I kind of like to think about this as a silverware organizer, right? You know, it says, oh, I got a fork, it goes here. I got a knife, it goes there. I got a spoon, it goes there. I got a long fork, it goes there. So that's kind of what the classifier does. It figures out where to go and where to put things in the hash table. Then we have the constructor reference, which in this case creates a tree map, but you could have it be something else besides a tree map. There could be other kinds of maps, for example. And there's all kinds of interesting maps. There's linked hash maps, which are very clever because they use hashing to put the elements in the table quickly, but then they keep track of the order in which the elements were inserted. So you can traverse through a linked hash map based on the insertion order, not the order that things were put into the table. And that can be useful if you're trying to hash stuff that had a predefined order that you care about, like maybe it was sorted, for example, and you want to be able to print the results out in sorted order. And then the third parameter here is something very interesting called the Downstream Collector. And we'll talk about these in more detail later in the course. But a Downstream Collector is what's going to be applied in order to figure out what the value should be. And in this particular case, we're using the summing long Downstream Collector, which will have the same effect that the second parameter did to the toMap method, which is to go ahead and put this into that the values will end up basically being a list of longs. So not a list of longs, it's going to sum them together. You could make a list of longs also, but this is going to sum the results into a long value. And we'll talk more about downstream collectors. They're very powerful and very cool, but take a little bit of time to get your head around it first. There are also other things that you can use to convert strings into streams. So here's an example where we're going to use the pattern matching features, the regular expression features in Java, using the comma as the separator. And then we're going to give it a string, which is all the characters in Hamlet. And we're going to split this as a stream using the comma as the splitter. So that's going to go ahead and split things up. So we don't have to do some other technique. If our input comes as a string, we can just break it up this way. And then we use the same grouping by mechanism we looked at before. So that's the end of the discussion of the collect terminal operations. Believe it or not, even though we spent a fair amount of time going through these things, there's even more to say. And we will say that later, because I'll give you examples of how to define your own collectors. We've been talking here primarily about the ones that come out of the box, the predefined collectors. But you can make your own collectors. You have to know why you would make your own collectors. But one of the common reasons to make your own collectors is to be able to have them work efficiently in the context of parallel streams. And there's a whole thing called concurrent collectors that we'll talk about later that give you much more control over how it all works.